All right, now we're going to look at a more sophisticated application of L'Hopital's rule. We're going to look at using L'Hopital's rule when we really don't have any other way to evaluate the limit except for using it. So this is the kind of questions you might expect on the AP exam because they really are able to target whether or not you've studied this theorem. So just by review, L'Hopital's rule says that if we have a limit of a quotient, and that limit could be approaching a real number or an infinity, if we get an indeterminate form such as 0 over 0 or infinity over infinity, then we know that the value of that limit, if it exists, is equal to the limit of the quotient of those derivatives. So let's take a look at this one. Consider we've got a function f of x squared minus 4x to think about this time. And let's assume we know these following things about f. We know that f of 1 is equal to 4. We know that the derivative of f at 1, f prime of 1, is negative 2. F of negative 3 is 5. And f prime of negative 3 is 1. And we're given this limit. We're given to evaluate the limit as x approaches 1 of x squared minus 4x minus f of 1 minus 1 and over x minus 1. So let's just go ahead and directly substitute that. Well, I'm going to plug in a 1 for x here. And if I plug in a 1 for x, I get 1 squared is 1 minus 4. Well, that's a negative 3. And we know that. So that's f of negative 3 is 5. And then f of 1, which is 4, well, 5 minus 4 is 1, and 1 minus 1 is 0. And then on the bottom, clearly 1 minus 1 is also 0. So there's really not a lot I can do here. I can't do any kind of factoring out or algebra or anything like that because I don't have the equation for f. And that happens a lot. We oftentimes have information about f at a specific moment in time or the derivative of f, but we don't have the equation. So it's an important skill to have. So let's go ahead and use L'Hopital's to figure out this limit. And in order to use L'Hopital's, we're going to need to establish that L'Hopital's applies. So let's show that the limit as x approaches 1 of the numerator is one of our values that we need. And if the numerator is 0, we need the denominator to be 0. If the numerator is infinity, the denominator would have to be an infinity. All right, so let's plug in 1 for x. I get f of 1 minus 4 minus f of 1. Now, f of 1 was 4. Okay. All right, 1 minus 4 is a negative 3. And f of negative 3 is 5 from this right here. So 5 minus 4 minus 1. Well, that's definitely 0. Okay, so we've shown that. Now, because the numerator is 0, we need to show that the bottom is 0 as well in order to apply L'Hopital's. Let me just do the denominator in a different color here. Use blue. Okay, so we have the limit as x approaches 1. And that's x minus 1. Get rid of that little mark there. There we go. X minus 1. Okay, that's easy to do. You just plug in 1 for x and we get 0. Okay, so because the limit of the numerator and the denominator are 0 over 0, we definitely can apply L'Hopital's. So let's do that. So by L'Hop, we know that the limit as x approaches 1 of all that over all this. Now, if this limit doesn't exist, it must be equal to the limit as x approaches 1 of the derivative of the numerator over the derivative of the denominator. So now we need to take the derivative of the numerator. Well, the derivative of f of x squared minus 4x is f prime of x squared minus 4x, because that's how we take the derivative. We take the derivative of the outside first, and we leave the inside exactly the same. But now I'm going to multiply by the chain. And watch carefully how I put the chain in parentheses. That's so important. The derivative of x squared minus 4x is 2x minus 4. Very important that we put the chain in parentheses, or else we'd only be multiplying by the 2x, not the 2x minus 4. Okay, now we need the derivative of f of 1. Well, that's just f prime of 1. So minus the derivative of f1 is f prime of 1. And the derivative of 1, well, that's a constant, so that's just 0. Remember, we are able to take the derivative of each one of these parts one at a time, because they're separated by addition and subtraction. You can't do that with multiplication or division, but we can take the derivative of each part of several terms. Each term one at a time. Took the derivative of this term, and we got that. And the derivative of f of 1 is f prime of 1, and the derivative of 1 is 0. Okay. Now the derivative of the bottom, the derivative of x is 1, and the minus 1 goes away, so it's just that. So now let's try direct substitution again. Plugging a 1 in for x, I get f prime, and we plugged 1 in here a couple times. That's 1 squared is 1, minus 4 is a negative 3. So this is just f prime of negative 3. And then we have 2 minus 4 is a negative 2. And then we have f prime of 1. Well, I'm just going to leave it as f prime of 1 for just a second, just so that I do all my plugging in at the same time. Now, I could have left this 2x minus 4 as just 2 times 1 minus 4, but it was pretty simple, so I went ahead and did it. But to get full credit for a problem like this, we can't leave our answer in terms of f of something. We do need to go in there and find them. So let's find f prime of negative 3. Well, that's 5. So f prime of negative 3, that's 5. We were told that. And then we're going to have that times negative 2. And then f prime of 1, up here we can see f prime of 1 is, f prime of 1 is negative 2. So that becomes minus a negative 2. And you can just leave your answer just like that. If you're curious, it's a negative 10 plus 2 is a negative 8. And that's it.